Hello, welcome back. In this segment, I'm going to talk about an interesting problem that was given to our grad students at the University of Maryland. Um, the problem is related to RSA, and let's go straight into the problem. Alice and Bob are using a buggy implementation of RSA. So there's a bug in the RSA implementation somewhere. Um, I'm assuming you're familiar with how RSA works. So this is the raw RSA without any padding, whatnot. But the problem is not so much related to padding per se. It's related to the mathematics behind RSA. Okay. So in RSA, we have the private and public exponents. The private exponent is D, the public exponent is E, and they are mathematically related to each other. Okay. E dot D is congruent to 1 mod phi of n. Phi of n is the Euler's torsion function. Okay. So in case you're not familiar with RSA, I recommend you to read about it or watch other videos. Okay. All right. So where is the bug now? The encryption function is given here. It takes a message and writes it to the exponent E, the public exponent E, right? If Alice wants to send a message to Bob, Alice will use Bob's public key, which is basically the pair E and Dn, right? So she will take the message M, rise it to power E mod N, meaning M power E when divided by N, the remainder is the value C. She send it to Bob. Bob will decrypt the incoming message using the algorithm given below, but the bug is here. The bug is over here. We are using C power D mod Q, which it should have been C power D mod N. Okay, that's the bug. Let's see what the problem we are asked to solve. We are asked to solve, prove or disprove that encryption of the message M and then decrypting it, meaning get back the original message, is same as the message if M is less than Q. Okay. In other words, it says prove or disprove that this assumption is true or not if M is less than Q. Okay. So that seems to be an interesting problem. Okay. We have a buggy implementation, and we need to find whether this bug will disappear if our input message M is less than Q, meaning we tried for many M less than Q. If the decryption of encryption of M is M, we know it's very likely right, otherwise wrong. So how do we go about it? Okay, let's start writing the details of this problem step by step. So I'm going to do like this. Take the definition of this line and write it here. Okay. So what is Alice sending to Bob? She's sending the value C, right? So how is C computed? C is nothing but M power E mod N. That means she takes her M, right? The message that she would like to encrypt. In real life, in practice, M should not be directly encrypted. You have to first pad it to introduce some randomness. But for now, that's not the main topic. Okay, we are just looking at the raw RSA function. Okay, right. So this is basically the definition of C. How can we rewrite this? Well, we can definitely rewrite it and get rid of mod N by rewriting like this. What it means is that C is nothing but some multiple, say S multiple of N, right? And we need to, okay, let me rewrite it this way. C is nothing but M power E minus some constant S, we don't know what that is, time N. I think that makes sense because that is the definition of mod N, right? What it means is that, for example, you have 8. Let me write it here as an example. 8, you do mod 3. What you will get is 2, right? And so 2 is the remainder. Okay. So we can also say 2 is equal to 8 minus quotient. The value of S in this case will be 8 divided by 3. The quotient is 2 times 3. Okay. All right. That's basically it. This is the S value that I wrote it here. Okay. All right. So that's the definition of the mod N definition that I am applying to C. So what is Bob doing? Bob is taking the C and rising to power D. So C power D mod Q is what he's going to compute. So let's think about what is the value of C power D mod Q. Okay. Right. This is nothing but M power E, because C is same as M power E minus S times N, right? Power D mod Q. Okay. And now we can easily solve this problem. What is N? n in RSA is nothing but p times q. So this is nothing but m power e minus s times p times q, right? Power d by mod q. Okay. Now we can easily apply binomial theorem to this. Even if you don't know binomial theorem, it doesn't matter. When you have mod q and you have a multiple of q, that term will be 0, right? This is the only term that is multiple of q. That means this term will become 0. So we can write it as m power ed, right? Mod q. Okay, so now we can easily solve this problem. What is E and D? E and D are related by this nice relationship 1 phi of n, which means this is nothing but m for I can write it as 1 plus some constant. We don't know that constant. Let's call it k times pi of n. What is pi of n? Pi of n is Euler's torsion function. So I'll write it here. Pi of n is nothing but when n is a composite number, pi of n is easy to find. It's nothing but p minus 1 q minus 1, right? So this is the definition of pi of n. So we can now substitute pi of n over here. We get e times d is, let me expand this again. What is e times d? E times d is nothing but 1 more than k times pi of n. Okay. That's basically the definition of e times d anyways. Okay, so this is basically what we have. And if we plug it in, we get over here e times d is nothing but k times p minus 1 q minus 1 plus 1. I already wrote in mod q. Okay, all right. Now we can just write this as m in mod q. Okay, so you have to write the mod q over here. Is same as m times, because of exponent, I can write it as m times k. And now is the trick. I'm going to write it as p minus 1 power q minus 1. This is perfectly fine because of the exponent rule. Again, also in mod p. Okay. And now this is nothing but m, because this term is 1. Okay. Why is this term 1? Okay. Here is the little theorem of Fermat. It applies for any group. If you have a term a, and if you raise it to a prime p minus 1, okay, you get 1. When you divide it by p, the remainder will be 1. Okay, there's one more constraint, that a has to be not multiple of p. Okay, otherwise this won't hold. Okay, if a is a multiple of p, you know this part will be 0, so 0 cannot be equal to 1. So a should not be multiple of p. That means in our case, they gave a constraint that m is less than q. Okay, which means this whole term. Anyway, let me finish this first. So m power k p minus 1 power q minus 1 is 1 in mod q, because I have written something power of q minus 1. So what I'm left with is m mod q, which is nothing but m, because they gave a constraint that m is less than p, m is less than q rather. Okay, so that's basically correct. Even though there's a bug in the program, the bug is only affecting if m is greater than or equal to q. If m is less than q, we are good to go. That's what we have proved. Okay, let me summarize this very quickly. I've just used the definition of encryption function, which is m power e mod n, which means the constant c, or the value c, ciphertext c, sent by Alice to Bob is m power e minus s times n. We don't know what s is. S is some non-negative integer. It's like this quotient when you divide, right? That's basically the yes. Okay. And what Bob is going to do is he's taking c power d mod q. C can be used, can be replaced as m power e minus s times n power d mod q. And we know n is same as p times q. So because of modular arithmetic, this term will get cancelled out. We are left with the m power ed mod q. Ed is same as 1 plus k times p minus 1 q minus 1. I explained it here. Why? Because that's the definition of mod with phi of n. and I'm splitting the exponents because of the exponent rule. And we know this particular term that is in the box is 1 because of this nice little theorem of Fermat. Okay, if P is prime, A power P minus 1 is congruent to 1 mod P. For all A less than P, we know that that's true. Okay, so we have just proved that. That's really nice, and we also made use of that. Okay, wonderful. That's basically the proof for this particular problem. So it's an interesting problem in the sense there's a bug in the code. It works correctly for all M less than Q. And if you want to try this in a programmatic way, I will show you that as well. Okay, so what I'm going to show to you is my little program that will, okay, as a matter of fact, the little program is over here, and I will clean my screen now. Okay, so I took some published prime numbers P and Q online. This, if you go to RSA numbers website, you see a lot of published primes. So I just took 2 of the primes, small primes, just for demo purpose, not for production use. And then I compute P times Q, that's the modulus n, and I use the standard public value E. I compute phi, and then I compute an inverse of E mod phi that will give us the exponent D. And I'm going to show to you, select any M, say for example M to be Q minus 10, encrypt it. But you see the decryption, I'm using Q instead of N. That means I'm introducing a bug, but this assertion is still true. I can successfully decrypt. So let's run it. Yeah, there is no assertion failure. Let me show you, just introduce a failure in my assert. Yeah, it fails. That means this must be incorrect. Okay. All right. So of course, this is not the way you prove things, but I just want to show you one example where I select an M less than Q and I can decrypt it successfully, even though I'm using Q instead of N. All right, that's all. Thank you very much.